All right, so we're going to talk about the applications of the derivative. And we've already talked about one of them, which is L'Hopital's rule. So now we're going to talk about a different one. And this one is something that we would use in physics. And in fact, if you know your kinematic formulas and you remember doing kinematics, then you'll remember this because it's very similar to that. It's just that we're going to use calculus instead of using our kinematic formula. So here's what we're going to sort of think about. If you take velocity and acceleration and you think about them as rates, because they are, velocity is meters per second, acceleration is meters per second squared typically, then you can kind of imagine that they must be the derivative of something, because the derivative is the instantaneous rate of change. So we've already seen that, right? The derivative is the rate of change. So if we think of the displacement, the distance as well, but the displacement, because it's a vector, generally is what we use. If the displacement is a function of time, then the rate of change of displacement, so s prime of t, the derivative of displacement, represents something. It represents the rate of change of displacement over time, and we've called that velocity because it's going to be in meters per second, or some value of measure of length versus a measure of time. So it could be, kilometers per hour, but it's going to be something like that. So we can understand that the derivative of velocity, the derivative of displacement is velocity. So here's what we end up with. This is the piece of information that we need to understand to solve physics problems. So projectile motion problems like this. So after t seconds, it says the vertical height in feet of a ball thrown upwards. So we're talking about feet, and the reason we're talking about feet is because I took this from the textbook that we're using, and the textbook that we're using is American, so it uses feet and miles and those things. But it gives me a height function, and it says determine the initial velocity. So before, you would have to have some other form of information. So you'd have to, say a was negative 9.81 because it's the acceleration. The initial height was 640, and you could find the initial velocity somehow that way. But now what we can do is we can say the velocity is just the derivative of height. So it's just minus 32t plus 96. And then what we want as the initial velocity is when the time is 0. So we go minus 32 multiplied by 0 plus 96, and that gives me 96. And it is in the unit of feet per second. So that's the initial velocity. Okay? So it's a pretty simple derivative, and most of them are because they're just polynomial functions, they're just quadratic functions, but it's a nice little application of it. Now the next thing says find the maximum height. So the maximum height, if you think about a maximum, if you kind of draw a parabola, the maximum, when it happens, has a slope of 0. Okay, the slope at the maximum, that's supposed to be touching, but the slope of the tangent line of the maximum is 0. So what we know is that the max height, there is no velocity. So the max height, you remember this from physics, hopefully you do, means the velocity is 0 at that point because it's going to come up, it's going to stop instantaneously, and then fall. So all we do is we take our velocity function, our v of t, which is minus 32t plus 96, and we set that equal to 0, and we solve. Excuse me. So we're going to get 32t is equal to 96, and that means that t is 3 seconds. So the max height occurs at 3 seconds, but that's not the max height, that's just where it occurs. So now we have to go figure out, okay, what's h of 3 then? So it's minus 16 times 3 squared, and then, minus 16. And if we jump back here, I gotta remember it's plus 96t and then plus 640. So plus 96 times 3, and then plus 640. So 3 squared is 9, so we get minus 16 times 9 plus 96 times 3, that's 270 and another 18, so 288. And then plus 640, 16 times 9, that's 90 and 54, so it's 144, plus 288, and then plus 640. So if I add those all together, it gives me what, 784 feet. Okay. So that's the maximum height, and it occurs at 3 seconds. All right, and then the next part says determine the velocity of the ball when the ball returns to Earth. So now I want to know what's the velocity when the height is equal to, whoops, when the height is, when h of t is equal to 0. So I go minus 16t squared plus 96t plus 640 equals 0. I got to figure out when that happens. I'm going to factor out a negative 16, and that's going to give me t squared, and then minus, I think 16 comes out of 96. How many times? 6 times. So that's 60, and then I think it comes out of 640, and it would be 16 times 4, so 40 times. And then we got to factor that. Okay, so we're going to go minus 16 multiplied by t minus 10 and t plus 4. And so we end up with 2 possible answers. T is 10 seconds or t is negative 4 seconds. But of course, you can't have a negative time. So it's got to be at 10 seconds. So then we want the velocity when that happens. So we go, what's the velocity at 10 seconds? So it's minus 32 multiplied by 10 plus 96. So I get negative 320 plus 96. And that is negative 224. And that is in feet per second. Okay, so that is the velocity when it returns to Earth. And it's negative because it's indicated that it's going down. Okay, so that's the concept in terms of velocity. And that's a pretty simple example, but it's the same kind of thing for all of them. It's solving what you guys are used to in terms of physics questions, but with derivatives. Now, the only other statement that might be added in there is that the velocity, when you take the derivative of the velocity, it's equal to the acceleration. Okay, and if you then sort of translate that back to the fact that the velocity is the derivative of displacement, that means the second derivative of displacement is acceleration. Okay, so if I go back to my example and I say, okay, well, my h of t was minus 16t squared plus 96t plus 640, and then my v of t was minus 32t plus 96, then my a of t then is the derivative of this, so it just becomes negative 32 feet per second. Okay, and you might be saying, well, I thought the acceleration due to gravity was negative 9.8. It is in meters per second squared, but this is feet per second squared, so it's a little bit different because the unit's different, but it's that same thing we're used to. But that's a constant, right? And which makes sense because that is a constant in terms of being on the Earth. You're always going that acceleration. So you can sometimes see questions that you're used to in terms of it being projectile motion and being a quadratic. Sometimes you'll see the velocity reported as something to do with a trig function or something like that. And we'll look at more of those together in class. But you basically just have to understand that when it comes to kinematics, we can solve them using our physics formulas, or we can use this information that now that we know the derivative and how to take the derivative of displacement is velocity, and the derivative of velocity is acceleration. And what's kind of neat is you can kind of see this happen even in the kinematic formula. So if you think about this formula, okay, which you probably derived in physics class, if you take the derivative of that, if you take d prime with respect to t, then v0t just becomes v0 because the derivative of t is 1, and that's considered to be a constant. And the 1/2 a stays in front because we're treating that as a constant, but the derivative of t squared is 2t. And what we end up with is these 2's cancel, and so we end up with this statement here that it's v0 plus at, and that d prime, we've already said, is it's the velocity. So you can see how taking the derivative of this kinematic formula gives you that kinematic formula. So they are related to derivatives. Now, when you did them in physics, you would have not talked about derivatives because you didn't know calculus. But you will find that, in fact, a lot of physics can be done with calculus. And the more that you know about calculus, actually, the more physics makes sense. So I'm going to leave it there. We'll do more examples in class, but that's the concept, really. And all it is that you have to understand that the derivative of velocity is acceleration, the derivative of displacement is velocity, and therefore the second derivative of displacement is acceleration.